Welcome to our first keynote, Intelligent Architecture for Intelligent Machines. Because current computers are not designed efficiently. If we were to make them have more computing power, use less energy, and be more secure, we would truly unlock the power of computing. Now, before I introduce our speaker, it's time for the fastest finger first quiz, which means you have to answer a question from me on the chat on the right-hand side. And the first 5 people to answer correctly will receive points, and we will announce the winner with the most points at the closing session tomorrow. And the question for today is, you can find it below, where is our speaker a professor? Where is our speaker a professor of computer science? Go look below and type the answer in the chat. And the first 5 people to answer correctly will receive the points for this part of the fastest fingers first. You can find the chat, of course, on the right-hand side, like always. You can put questions in there as well, but for now, I'd like to know, of course, the station, where is this speaker a professor? Yeah, and the first correct answers are in. We have a couple of people who are really quick, and the first 5 of you will receive the points. Thank you so much for participating. Very important, we will keep using the chat. So if you have any questions for the speaker, please use the chat as well. And as most of you have it correctly, Onur Mutlu is a professor of computer science at the ETH in Zurich. His group has done a lot of work designing fundamentally secure and energy-efficient computers, and will offer suggestions in which direction to take future computer design. Onur Mutlu. Onur, welcome. Take it away, and I'll come back to you for when we have questions from the audience.
Okay, sounds great. So let me pull my slide screen over here. Okay, thank you everyone, and thank you very much for the organizers for inviting me. I'm going to talk about intelligent architectures for intelligent machines. I assume you can see my slides at this point. Okay, so I will, basically that's what my talk is entitled, Intelligent Architectures for Intelligent Machines, and hopefully I'll give you my opinions on what we are doing not so well in the designing of today's computing platforms and what we can do better. Okay, so I will click through my slides. I assume you're seeing them at this point because I don't see them for some reason. There's some delay. But basically, today's computing systems are bottlenecked by data. And data is really key for many workloads. Artificial intelligence, machine learning, genomics, all important workloads are all data intensive today. They require rapid and efficient processing of large amounts of data. And data is increasing. Today, we can generate more data than we can process in many applications. And I'm going to show you some examples of these applications. These are some applications you may be writing or dealing with, or certainly executing when you write an email, for example, that goes to a data center. And these workloads are all bottlenecked by data, and data causes performance and energy issues. And if you look at the mobile end, you are also using many of these workloads. In fact, some of us are using these video playback and capture workloads right now. And there's certainly machine learning processing going on. We're all using our web browsers. Actually, all of these workloads are being used at the moment during this conference, and they're all bottlenecked by data as well. So the data that's flowing through our computers right now are bottlenecking our performance and consuming a lot of energy. And if you look a little bit more into the future, genomics is an up and coming workload, genome analysis. You can do a lot by understanding the genomes of biological species and certainly humans. And we've made a lot of strides in genome analysis, especially technology, to sequence genomes. You can see that the slide is a bit out of date, but the number of genomes that we sequence, that we're able to sequence at low cost is growing exponentially. And this is generating a lot of data. But today we are very much computationally bottlenecked in terms of what we can understand from these genomes. And as a result, our scientific discoveries and medical advancements are actually quite bottlenecked by what we can do to analyze the genomes. I'm not going to, basically data is a performance and energy bottleneck in these devices. And these devices are actually becoming smaller and smaller. This is the nanopore sequencing technology. Actually, this sequencing technology is used very heavily on COVID-19 understanding today. There's a lot more to do, of course, by comparing, for example, the COVID-19 genome to many, many other genomes that are out there, and to understand the interactions of different humans to the different strains of the viruses. So there's a lot of data that you can imagine that can be collected with these small devices that you can hold in your hand. But unfortunately, the devices are not powerful to do analyses. In fact, we don't have a lot of powerful devices to do these analyses, so the data that we produce goes to data centers, and you actually lose a lot of efficiency and energy in communicating that data to the data centers. And as a result, the analysis that you get may take weeks or even months, depending on the difficulty of the analysis that you have. But basically, genome analysis is an upcoming workload, and this is one example of the upcoming workloads, in my opinion. If you're interested in this, I'm happy to talk about it. We've written papers on this topic. This is a survey paper that we have recently published, and I would invite you to take a look at it if you're interested. And certainly there's a lot to do in this area. We have been building frameworks to actually accelerate genome analysis so that we can hopefully enable doctors to make decisions within real time. Let's say they get the genome of a patient, for example, and after that, they can figure out quickly what drug to administer, personalized to the patient within a minute or so. Our goal is within a minute, of course, or seconds, if that's always better. But today we cannot do that within a day or even 2 days, even with the most powerful processing engines that we have today. So we're looking at a lot into acceleration of genome sequence analysis today. And the future is very mobile, as you can see over here. These devices already exist, but not the computational efficiency and the power to process the data that's coming out of these devices. And if you're really interested, we have also talks related to this topic that go into more detail. I'm not going to cover genome analysis in this particular talk, but I use as an example up and coming application that's going to be very important in the future of our lives, and I believe humanity as well. So if you're interested, you can actually take a look at the lectures on our YouTube channel, as well as the particular lecture that I pointed to. So my point with all these workloads is today's workloads are extremely data intensive, and data overwhelms modern machines. It overwhelms the storage and memory capability, the communication capability, and the computation capability. And in the end, it greatly impacts robustness, energy, performance, and cost, and security, as we will see. Essentially, all metrics that we really care about in the design of our systems. And I'm going to talk about security and safety in a little bit to motivate something, and you will see that. And clearly, security and safety are going to be extremely important for us in life-critical or safety-critical applications. So certainly, genome analysis could be safety and life-critical at some point, depending on when you need that information. But self-driving cars are essentially safety-critical applications that are actually very important for us going into the future. Now, let's take a look at a computing system from the very basics. Essentially, a computing system consists of 3 key components: computation, communication, and storage and memory. And essentially, today, we have actually heavily optimized the computing unit over time. Let me see if I can actually have this laser pointer that you can see. I'm not sure if that works. Okay, basically, sorry about that. If I have to go back to the previous slide. Okay, basically, today we have heavily optimized the computing system. And if you look at a computing system underneath, because we are very processor-centric, we need to bring the data into the processors before we can process them. Most of the system is really dedicated to storing and moving data today. Essentially, these computing systems are called computing systems, but if you look at the hardware real estate, most of the hardware is really dedicated to like more than 90% of the hardware in a computing platform is really dedicated to storing and moving data. And that's going to be one of the important things that we will discuss in this talk. Essentially, data is a big performance energy bottleneck today. Let me give you one result that we have found together with Google by doing research over the course of 1.5 years with them. Basically, we examined some mobile workloads that essentially everybody uses that I mentioned earlier. And we found out that more than 60% of the total system energy while executing these workloads on a state-of-the-art mobile device like a cell phone is spent solely on moving data between the processor and the memory. And we're going to talk about potential solutions to this problem. Okay, so my axiom, given all of this background, is that an intelligent architecture has to handle data well. Of course, then the question becomes, how should we handle data well? So I believe there are 3 aspects of it. I'm not going to focus on all aspects in this talk. I'm going to focus on especially the first one over here that I put up. We want to ensure that data does not overwhelm the components of a system we design by designing intelligent algorithms and intelligent architectures or platforms. And more importantly, doing both at the same time, essentially designing whole systems, platforms, all the way from algorithms to architectures to devices to enable this. Okay, the second aspect, which I'm not going to talk as much about, is that we would like to take advantage of vast amounts of data and metadata flowing through the system so that we can continuously improve the decisions a platform makes by learning from the data and metadata that's flowing through the system. And third, we would like to understand and exploit different properties of different data that's flowing through the system. So not all data is equal. Some data is video, for example. Some data is audio. Some data is genomes. Some data is RNAs, for example. And they're all different. They all have different characteristics. And we should probably understand these characteristics really well and exploit them at the very basic levels of the computing platform and architecture and our algorithms so that we can customize our algorithms and platforms to these characteristics so that we can maximize the efficiency and performance we get. Okay, so these are three things that I mentioned. And corollaries, if you look at architectures today are not good at dealing with data because they're designed to mainly store and move data as opposed to compute. They're processor-centric as opposed to data-centric, essentially. I'm going to talk a lot about this in this talk. What I'm not going to talk as much about is the other two. Today's architectures are not good at taking advantage of vast amounts of data and metadata that's available to them. Essentially, they do not learn much. They ignore lots of data. For example, I like using the example of my cell phone. My cell phone, I've been using it for some time, let's say 6 years. And it has some component in it. It's a memory controller or a thread scheduler, pick either one. And this memory controller or thread scheduler has seen a lot of events and has essentially interacted with me many, many times without knowing, of course. And it hasn't learned anything from that interaction. Basically, it's employing the same fixed policy that the hardware designer or the software designer dictated it to do when it was designed. Over time, over the course of 6 years or even milliseconds, it didn't learn anything basically. Whereas it could have learned a lot from my behavior and customize itself to my actions and also to the data that's flowing in the system. So I believe we need to design platforms that learn from what happens. And we're not doing that well today. But again, as I said, I don't have time to talk about this data-driven aspect. So we need more data-driven decisions in our computers. And the third one is architectures today, as I mentioned, are not good at knowing or exploiting different properties of different types of application data. They don't know, for example, the privacy properties, security properties, compressibility properties, error tolerance properties of different data. As a result, they're designed to treat all data as the same. And they don't make data-aware decisions that can maximize performance or maximize efficiency or maximize security or privacy, etc. So basically, I think going forward, we need to design data-aware architectures as well. So in the rest of this talk, I'm going to focus especially on this data-centric versus processor-centric paradigms and talk about how we can design much more data-centric paradigms going forward. But this doesn't mean that data-driven and data-aware architectural or platform design paradigms are not important. We just don't have enough time to cover all of them today, I think. And I will point you to some other resources if you're interested to take a look at those paradigms. So let's get started. Let's talk about these data-centric or memory-centric architectures. So there are a lot of properties that a data-centric architecture requires. You don't need to read the entire slide. I'll give you very quickly. I'm not going to go into the details of all of them, but basically we want to process data where it resides. We don't want to move data a lot in the system. Remember that we're moving data a lot in the system. As a result, more than 60% of the system energy is spent on data movement. We would like to cancel that. We would like to make sure that that doesn't happen. On top of that, we would like low latency and low energy access to data, low cost data storage and processing, and intelligent data management, all of which are important. But again, I'm not going to go into details of it. I'm going to mainly talk about processing data where it resides. Essentially processing data locally, wherever it's generated. And this applies as a macro principle, meaning if you have a genome sequence analysis device, don't move the data to a data center to process it. Process it locally so that you can minimize the energy waste and also maximize the performance. Similarly, within a computing system, within a computing platform, you have a computing unit and also a data storage unit. Don't move the data between them. Process the data wherever it is, in the hard disk, inside the memory, inside the caches, and minimize the data movement as much as possible. So I'm going to motivate this a lot. But this is an old idea, I should mention. This idea has been proposed in the 1960s. And this is a seminal paper by Harold Stone, if you're interested in taking a look at it. But today we need to re-examine the idea. The idea has never really taken off, if you will. Today we have a huge push from technology and pull from applications that I will describe as to why we should really be re-examining this idea in a different way. And the push from technology is that the main memory technologies that we use to design our computers today is at jeopardy. Basically, it's not scaling very well. As a result, industry is right now investigating controllers that are close to DRAM, close to memory, and industry is open to new memory architectures as well. And I'm going to give you examples of this. This is a hybrid memory consortium where you can have logic very close to a memory. This is another example of it. And they're actually experimental devices. And I'm going to give you more examples of these now commercial devices actually that are putting data processing inside the memory chip. So when we first started looking at this topic, it was around 2011 or so, and I was invited to give this talk at an industry conference, International Memory Workshop, where I argued that memory scaling is going to become a much bigger problem. So as we try to increase the capacity of memory, we're going to have a lot of problems. And now I'm going to show you some evidence that we gathered within the course of last 7 or 8 years after that talk. I'm going to give you some examples from the field. This is one study that we did with Facebook, for example. And what we did in the study is we analyzed all of the failures that their memory gets in their servers worldwide. And this is a lot of servers that they have in their data centers and a lot of memory. And basically what we found out that the memory that's employed, as the memory that's employed inside the server gets denser, this is chip density on the x-axis, the failure rate of the server increases. Essentially, there's a very positive correlation between the chip density and the server failure rate. Why does this happen? Because cells you have in memory are close to each other, and as a result, they're very noisy, they're smaller also, and as a result, they're more vulnerable to reliability problems and noise problems. And if you're interested, you can take a look at our paper that details it. Later, we also built infrastructures to understand these issues, and these are FPGA-based, reconfigurable computing-based infrastructures, where you can test memory at scale. As you can see, these are just examples. You can find all of this information online because we open source this infrastructure as well. And in fact, you can play with it. If you're interested in playing with it, let us know, we can help you. You can test different memory errors. And while we were actually trying to understand the issues like reliability issues, latency issues, security issues that are happening with main memory, we stumbled upon something really interesting together with Intel. And this is essentially the fact that you can predictably induce memory errors in most memory chips today. I'm going to talk about this briefly a little bit to motivate why we need intelligent controllers, because this should not really happen. This is now known as the row hammer problem. Essentially, more than 80% of the chips that we tested, memory chips that we tested, were vulnerable to this problem. And this is really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And as a result, people are writing articles like this. This is Wired magazine. It says, forget software. Now hackers are exploiting physics. As you can see, this is actually a very nice high-level characterization of what row hammer is. I'm going to go into a little bit more detail as to what row hammer is in this slide. Basically, this is a disturbance error. Whenever you read memory, you're disturbing other cells around what you're reading. And this should not happen. So basically, whenever you read DRAM, which is the main memory that's used in all devices that I know of today, you're activating a row, applying high voltage to that row. And if you keep doing this repeatedly, read and then close, read and then close, read and then close, read and then close. And if you keep doing that repeatedly, essentially what happens in most DRAM chips, most memory chips today is physically adjacent cells that you're not supposed to be reading or writing at all get flipped, meaning they change their value. This could be data stored by other applications, by your own application, by the system. It could be security critical data. It could be essentially determining your permissions to access some of the other parts of memory. And that's what makes a security attack. Essentially, you're changing data that you're not supposed to change just by reading memory in a hammering manner. We call this the hammered row. We call these the victim rows. And when we did this study, we showed that more than 80% of the chips that are out there in the field are actually vulnerable to this row hammer problem. And this is a memory scaling issue because older chips did not have this problem, but younger chips were all vulnerable because cells were too close to each other, and the number of hammerings you needed to induce these bit flips reduced significantly when the cells became too close to each other and smaller as well at the same time. So clearly this is actually a security problem also because one can take over an otherwise secure system by exploiting these bit flips. I'm not going to go into the details in this talk since we don't have a lot of time for details. I'm going to point you to some further papers if you're interested in this. But basically we said that one could hijack your system by taking advantage of these bit flips. And that's essentially what happened. Later Google folks, Google Project Zero folks, found out about our paper, and they basically showed that you could take over the Linux kernel by exploiting these bit flips that are out in DRAM lurking. And other folks in the academic community showed that you could exploit these bit flips to gain the control of a remote server. Some other folks showed that you could actually exploit these bit flips to gain control of your Android phone. More recently, people have shown that you could actually induce these bit flips in neural networks, which are supposed to be the basis of self-driving cars, for example, or anything that learns from the environment. And they basically showed that if you can induce these bit flips in a neural network, you can reduce the accuracy of a neural network from 90+% to 10% or so. And as a result, the neural network that was making good decisions before could make completely wrong decisions. Meaning that if these bit flips actually get into our security critical devices, safety critical devices, then, and someone exploits them, then basically all of the advancement that we have done in machine learning can be circumvented, because the machine learning is not very useful anymore. That's why these bit flips are extremely important. And if you're interested, you can read the papers that we have written and others have written on this issue. This is a review paper on Rowhammer vulnerability that I would recommend. It covers actually the literature until late 2019. But to solve this problem, we actually really need intelligent controllers. And I'm not going to go into details of the solutions, but an intelligent controller around the memory would not let this problem happen by fixing the problem before it happens. And you can imagine many different solutions. I'm not going to go into details. These papers discuss some solutions. But before going into the solutions, the problem is actually getting worse. Essentially, new DRAM chips are more vulnerable to Rowhammer because the memory cells are smaller and they're closer to each other, even closer to each other. And existing mitigation mechanisms are not effective. So you can read some of the papers that were published in 2020. This is one example paper that basically shows that DRAM chips that are manufactured that are advertised to be Rowhammer free are actually not Rowhammer free. Basically, someone can circumvent these Rowhammer solutions that are advertised to be working to actually launch these Rowhammer attacks. Again, I'm not going to go into the details of this. There are also solutions that are proposed in the literature, which are currently being picked up by industry, but we have more ways to go on this. And if you're really interested, you might want to watch the Story of Rowhammer lecture that goes into a lot more detail on this particular Rowhammer problem, which is, I think, a fascinating problem in technology scaling and security. Okay. So basically, let me conclude this part of the talk by asking you the question: how reliable, secure, safe is this bridge? Some of you may know this bridge. This is actually over the Hood Canal. It's not over the Hood Canal. It's over the Tacoma Narrows, close to Seattle. But this doesn't exist because this is what happened to this bridge in 1940. Essentially, I would call this a bit flip in critical infrastructure. And we, as humanity, have been building bridges for thousands of years, let's say. But unfortunately, we get into these bit flips once in a while, and they become life critical. It's unfortunate, yes. But if you think about the computing platforms that we're building and how much we're relying on them, we should probably be thinking about those bit flips that are happening to bridges and make sure that those bit flips do not happen to the billions of computing platforms that are going to be all around us, many of which we're going to rely our lives on. And this is another example that I used. How secure are these people on this platform? I think we should be thinking about security as preventing unforeseen consequences going into the future, because we will literally be running, essentially driving cars like this, maybe not to the extent that Mr. Bean does over here, but we will be essentially leaving our lives to the decisions that are made by the artificial intelligence in these cars, and maybe robots as well, who knows. But if we have these bit flips, then we'll have problems going into the future. So essentially, we need fundamentally secure, reliable, and safe computing architectures. And to be able to do that, I think we need to think a little bit more. We need to predict and prevent safety and security issues. One example I gave you earlier. And to be able to do that, I think we really need intelligent memories going into the future. Okay, so the takeaway is those bridges, we can actually do better than bridges because computing systems are relatively soft and we can have in-field patchability to avoid many failures. Okay, let me talk about the second part of in-memory computation, which is pull from systems and applications. So today, as I mentioned earlier, data access is a major bottleneck in many applications and systems. Energy consumption is a key limiter. We're going to talk about that. And data movement energy dominates computation energy. So in my opinion, the bigger question is, do we want a world that's sustainable and energy efficient like this? Or do we want a world where computing power actually destroys our sustainability and energy efficiency, along with potential other things that destroy sustainability and energy efficiency? I would argue that we would like a sustainable and energy efficient world, but we would also like the high performance benefits that come with computing so that we can solve all of the difficult problems that are ahead of us. But the problem is in the way we design computers. Today, data access is a major performance and energy bottleneck, but our current design principles cause great energy waste and also great performance loss because we're moving data a lot in the system. And the main problem is processing of data is performed very, very far away from the data, both in the macro scale as well as the micro scale. So let's take a look at the micro scale right now within a node, within a computing system. Basically, there are three key components, as I said: computing unit, communication unit, and storage unit. And we've heavily optimized the computing unit. We're very processor-centric. All data has to go to the processor so that we can process it. We cannot do anything inside the memory or inside the SSD, for example. And as a result, we have a problem with memory. And I'm not going to go through the details of it, but memory problem has been recognized by a lot of people. Dick Seitz is one of them, who is the chief architect of alpha processors. He realized it 20 years ago, and he said that memory subsystem is going to be the only important design problem going into the future. This is data from my own PhD thesis, where we, together with Intel, we showed that more than 50% of the time in a computing system is spent waiting for memory. And this is more recent data from Google. That was a paper that's related to my PhD thesis. But this is more recent data from Google that shows that more than 50% of the time, actually more than 60% of the time, is spent on the memory system in all of their data center workloads. So we clearly have a problem with memory, and we know it. Okay, sorry about that. It went a bit faster. So essentially, we have a grossly imbalanced system, which leads to energy inefficiency, low performance, and complexity. We try to cover up for this by making the software and the hardware more complex, and that leads to even more energy efficiency and low complexity, low performance and complexity. So basically, as a result, we have a problem with our systems where more than 90% of the system is dedicated to storing and moving data, and it's complex. Let's take a look at the energy perspective quickly. This is data that I borrow from Bill Daly. But basically, the key takeaway is a sophisticated arithmetic logic operation today is 20 picojoules, and a DRAM, a memory read or write, is 16 nanojoules. That's 800x difference. Basically, a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition today. And you can argue with the numbers, but there's a lot of literature that shows that it's 2 to 3 orders of magnitude difference. Which means that, does it really make sense to bring the data to the processor to the very cheap, energy-wise, sophisticated operation? Why not do the operation on the memory side? But because we're not doing that today, more than 60% of the total system energy is spent on data movement in many devices. Basically, I will argue that we do not want to move data because data movement is very performance costly and energy costly at the same time. So what do we need to do? We need a paradigm shift to enable computation with minimal data movement, compute where it makes sense, where data resides, and we want to make computing architectures more data-centric. So this is a big topic, of course. Basically, what we envision is we would like to be able to put a lot of data into memory, which exists today actually, because memory is becoming larger. And we would like the processor to ask memory, can you execute this function for me? And the memory says yes or no. If it says yes, it returns the results. Now, data movement doesn't happen. Data stays inside the memory or the SSD, and functions get shipped to the memory side. And there are many questions over here. I'm not going to go into the details of it, but how do you design the system overall? How do you design the software and the hardware interfaces, system software, comparison languages, algorithms, and theoretical foundations? This is a cross-the-stack problem, all the way from algorithms to devices. It's very exciting, but we can do it step by step also. Now, let me very quickly give you two approaches to reducing the data movement. One approach is going to minimally change the memory chips. The other approach is going to exploit some new technologies like 3D stacked memory. I'm going to show you some basic results in this, and then we're going to conclude. Essentially, let me start simple. Data copy and initialization is actually a very important application if you do bulk data copy and initialization. For example, if you have 1 terabyte database, and if you want to initialize it, today it takes a lot of time because you need to write data to memory. And Google recently showed that a lot of their data center cycles actually is spent on copy and initialization. So today, the way we're doing the copy is not efficient. Basically, if you want to copy one page to another page, we have to go through the CPU today. I'm going to go through this animation relatively quickly. I don't see the slides very easily over here. But basically, it's high latency because we have to go through the CPU. It's high bandwidth on the memory bus. You cause cache pollution, all kinds of pollution effects, and you cause a lot of unwanted data movement. So basically, it takes about 1,000 nanoseconds and 3.6 microjoules to do 4 kilobyte copy via direct memory access. Our idea is very simple. Just do it inside the memory. Don't disturb the CPU with all of these data copy and initialization. And this is clearly low latency, low bandwidth utilization, no pollution, and no unwanted data movement. As a result, we can actually improve the latency and energy of a 4 kilobyte page copy significantly. And the idea is very simple. I'm not going to go into the details of how we implement it, but the implementation internally inside the memory chip is also simple. Basically, it's 2 consecutive activates. You first activate the source row in the memory chip, which brings the data into the row buffer, and then you activate the destination row, which takes the data from the row buffer and puts it inside the destination row. That's essentially it. So 2 consecutive activates with minimal changes to the hardware. You can get essentially an order of magnitude latency reduction and close to 2 orders of magnitude energy reduction in memory. Ignore the right 2 bars over here. Those things are things that we actually fixed later on. But since we don't have time, I'm not going to go into details of that. But essentially, the key takeaway is you can improve performance and energy between 2 to 3 orders of magnitude by doing these simple changes such that memory can operate on the data. And if you're interested, you can read more detail, of course. But the thinking right now is that we're putting a lot of accelerators close to the memory chip. They're all processor-centric. Why not put some accelerators on the memory side or the SSD side where data is stored as well? So memory is similar to a conventional accelerator, essentially, in our thinking. Similarly, we can support other computation operations. I'm not going to go into the details, but we can use analog computation capability of DRAM and as well as emerging memory technologies. And basically, you can get 30 to 60x performance and energy improvements on these operations. And you can build an entire system that can execute workloads using these operations. And new memory technologies, in my opinion, enable even more opportunities because they're non-volatile. And you need to do, you can operate on data with minimal data movement. Let me give you one example result. Basically, this is an example result in our work on database acceleration. If you actually write your software such that it can execute inside the DRAM chip using the primitives that I mentioned and or not copy and initialization, you can improve the performance of the queries by 4 to 12x. This is end-to-end latency of queries, database queries. And I believe this is significant. And if you're interested in knowing more, you can take a look at the papers that I referenced over here. I have a lot of slides, but they're mainly references to the papers, as you can see, so that you can take a look at them later on. Okay, let me talk about this very quickly, and then we're going to conclude. Essentially, the second approach says take important applications and use devices so that you can minimize the data movements. At the time we started looking into this, which was around 2011 actually, we finished our first paper in 2015, we looked at graph processing. And graph processing is very, very basic essentially. It's expensive. Actually, at the core of any machine learning frameworks, also, logical graph is changed. If you do a lot of it, because memory durability, essentially you get access to the amount of computation. So we took the opportunity to exploit these logic layer that you can put underneath memory layers and 3D stacked memory systems as opposed to today's 2D planar systems. Now we're actually building 3D stacked systems, and other true three-dimensional technologies are also under development that are going to be more important. And we basically designed an architecture, which I'm not going to go into the details of, which minimizes the data movement. The data stays where it is, functions get shipped to the data. And if you're interested, we can talk more about it, but essentially you can read about it in this Tesseract paper. And it's a distributed system. You can offload the code into this distributed system from your host processor, and you can offload all of your graph analytics, and it gets executed on this. And the results are actually quite promising because we're not moving the data much, we're just moving the functions. And I'm not going to go into the details of it. Essentially, you do communication via remote function calls, just like we do distributed programming in data centers today, and we have some prefetching mechanisms as well. But basically, if you look at these systems, the Tesseract system is very different from existing systems. Existing systems all have the processor-memory dichotomy, and as a result, they're bottlenecked by memory in terms of bandwidth. But the Tesseract systems at the time had 8 terabytes per second memory bandwidth available to the cores that we designed. And the performance improvements are commensurate. You can see that on 5 important graph processing algorithms, you get 14x almost performance, end-to-end application performance. Later work upon our work, this is data from 6 years ago, as you can see, but later work actually shows that by doing better optimizations, you can get more than 2 orders of performance improvement, more than 100x. And I'm going to go into this. Energy improvement also measured. Essentially, we get close to 1 order of energy improvement.
Onur, you are dropping down a bit.
Okay.
Onur, we can't hear you at the moment. Your
can
connection
you
dropped a bit. Yeah, now it's stable
Okay.
again, but we kind of missed the previous slide and this slide. Could you go back to the previous slide and just briefly talk about it again so that everybody can hear?
Okay. Is it this slide that you missed?
Yeah.
Okay, sorry about that. I didn't realize that. Okay,
No,
so
that's why I
basically,
said again. No worries.
sure. Okay, basically, with this tesseract system, I will go one slide earlier. This tesseract system, we do inside the dichotomy.
Onur, you're dropping again. I'm sorry, Onur.
Okay, I don't know. Those over here. Is it better?
Now you're stable again. So let's try one more time, please.
Okay. Basically, with the system that we designed, processing and memory are coupled, and the performance improvements that you get on 5 important graph processing algorithms are close to 14x. Later works actually improved upon our results, and they actually optimize the system even better, and you can get performance improvements more than 2 orders of magnitude, more than 100x right now in these systems. Hopefully you can hear me. I'm going to go to the energy results.
Yes, we can.
And
Thank
energy
you so much.
Okay. Yeah, thank you. Sorry about that. Energy results are actually also quite commensurate. You can get an order of magnitude energy reduction in these 5 important graph processing workloads, graph analytics workloads. And later work also improved these results. You can actually get close to 2 orders of magnitude. So if you're interested, the paper has a lot more details. I don't have time to go through those details. But very quickly, you can also do these techniques in real mobile devices. This is work we did with Google a few years ago. And we basically analyzed the important applications in mobile devices. And I mentioned these applications earlier, actually. These are the popular consumer workloads that everybody is using a version of, if you will. Maybe it's not Chrome, maybe it's Safari or something else. But essentially, we found out that a lot of the system energy is spent on data movement, and we wanted to fix that problem. And we wanted to move computation close to data. And we realized that in many of these applications, a significant fraction of the data movement comes from simple functions. And we can offload these simple functions to memory, either to simple cores or sophisticated accelerators. And as a result, your performance energy improves by more than 2x. And this is a simpler approach. This is a more realistic approach in the short run. That's why the performance and energy improvements are lower than 14x that we showed earlier, but you don't change the system as much in this case. This is actually a more adaptable approach, if you will. I'm not going to go through the details, but if you're interested, for example, we looked a lot into TensorFlow. Machine learning frameworks are quite important today, and a lot of the energy is spent on data movement in machine learning frameworks, and we can accelerate them by more than 2x today. And if you're interested, you can read the paper for more detail. So let me cover some issues very quickly, and then we're going to conclude. Basically, we can do truly distributed GPU processing with processing in memory as well. These are some examples. I don't have time to go over them. If you're interested, I'm happy to talk about them. We can accelerate linked data structures like pointer chasing structures that are used in databases, for example, inside the memory. We can accelerate climate modeling very close to memory without moving data as much between memory and the processor. We can accelerate genome sequence analysis, as I mentioned earlier, approximate string matching that is used in genome sequence analysis as well as other applications, and a time series analysis that's used in many, many scientific studies while you're where you analyze data in time series that come at you. Astronomy is one example, for example. But to be able to do all of this, I believe we need to revisit the entire stack in the end, but we can get there step by step with minimal changes to the system. Okay, so if you're interested, we actually have a paper that talks about a very recent overview of, or provides a very recent primer on processing in memory, and you can find this on my website. And we also have written other papers. So the good news is industry is also designing this sort of processors. This is the UpMem company located in Grenoble, France. We work with them actually, and they put processing units inside the DRAM chips today. And this actually leads to significant performance and energy improvements compared to today's CPUs and GPUs. We'll actually release a paper about this soon. And more recently, Samsung, a big company clearly in memory, has announced that they're putting functions inside their DRAM chips to accelerate AI applications. And their systems, this was announced in February, basically they say they can accelerate multiply and accumulate operations inside the 3D stack memory, similar to what I showed you earlier. Industry is always lagging a little bit, but the good thing is they're actually looking at these problems and they're designing chips right now based on the ideas that were proposed in the past. And if you're really interested, you can actually take a look at the many detailed lectures that we provide on processing in memory. And this is one example tutorial that is much longer than this talk if you're interested in taking a look. So basically, we have a huge challenge and opportunity for the future. We want fundamentally energy efficient computing architectures that requires, essentially that requires architectures to be data-centric. We want fundamentally even higher performance architectures, and that requires architectures to be data-centric as well. So that all of this requires us to design systems with minimal data movement, in my opinion. So there are adoption barriers to processing in memory, which I'm not going to talk about. These are really important. But as long as we think differently, change our mindset such that we can have data-centric systems as opposed to compute-centric or processor-centric systems, we can get there step by step. So what I'm not going to talk about, as I said earlier, is data-driven, self-optimizing, self-learning, and self-improving computing architectures, and also data-aware, more expressive computing architectures that can understand the circumstances that they're dealing with. But I'm going to conclude at this point, since we don't have much time. Essentially, we've talked a lot about data-centric architecture design as opposed to processor-centric paradigm. I believe it's time to design these principled system architectures to solve the data handling problem, and we have a huge data handling problem in memory and storage. We would like to design complete systems to be truly balanced, high performance, energy efficient, and that requires intelligent architectures, which are data-centric, data-driven, and data-aware in nature. And we want to enable computation capability inside and close to memory. This can, hopefully, as I showed you, lead to orders of magnitude improvements in performance and energy, and maybe security as well, as we have briefly discussed. It enables new applications and computing platforms, and it will enable a better understanding of nature as well, because in my opinion, nature is by the way it looks, it's data-centric, data-driven, and data-aware. Basically, it's very specialized to data. And who knows what else it can enable. So I think these are the three principles that we should use, and maybe we should really get inspired from some of the principles that is used in the nature as well. Now, I don't claim to have all the principles, but I think we need to really do the research to revisit the entire stack to enable such systems. And these are some good principles that I know of, but I believe we need to add to these principles by keeping our minds open and making things much more data-centric, data-aware, and data-driven. So I will point you to some papers that I have discussed earlier. If you're interested, you can take a look at more. But at this point, I'll acknowledge our industrial partners as well as funding agencies who have supported all this research. And most importantly, I'll acknowledge my research group and collaborators who have done the research that I have actually mentioned in this talk. If you're really interested, you can take a look at our newsletters that are available over here. And everything that I mentioned over here in this talk is available online, freely, open source. You can find the source code as well as the papers online, as well as the videos, as I mentioned. So at this point, thank you very much for listening to me. I'm happy to take any questions you may have.
Thank you so much, Onur Mutlu. If you have any questions about building better computers or any of the issues you raised, please type them in the chat. We've got a few questions already. First, will we get access to the slides after the talk? Well, you've already shown where they can find them, but a video of this presentation, including the slides, will be shared as well. Udanai Botet asked, hello professor, does your approach completely eliminate the CPU, and how will processing in the memory be done?
So that's a great question, actually. The answer to the first one is no. Basically, CPU is still very good at executing compute-intensive tasks. So if, for example, you can put your data inside the CPU caches and you don't need to access memory in the task, you cannot beat a CPU by doing the computation inside the memory. So basically, our approach is complementing a processor-centric system. Basically, you want these paradigms, processor-centric paradigm and the data-centric paradigm, to coexist, because different applications, different workloads, and even a single workload will have different demands from the computing system at different times. So you would like to be able to use the best computing device, or let's say computing paradigm, that your workload benefits from. So essentially, in my view, the world is going to be much more heterogeneous going into the future. Some components will be able to do the processing inside the memory, inside the SSD, but we will also have Intel and AMD or like CPUs, NVIDIA like GPUs that are extremely good at the processor-centric paradigm, and we need those for those parts of the code and applications where we really are computation bound. And the second question is, how do we design the in-memory processing units? Essentially, that's a very good question, but I've given you some leads into how to design it. One way is minimally changing the memory chips by exploiting the analog computation capability. That's one direction. The other direction is you can actually have something like simple CPUs or accelerators or reconfigurable logic on the memory side. That's the second direction that I mentioned in the talk. Now, if you're really interested in knowing more about this, I would recommend watching some of those lectures and reading some of the papers, because that goes a lot more into the detail of the computing unit design, which really we don't have time for. But I'm also happy to take any emails if you're interested in knowing more. Thank you.
Okay, thanks so much. We have a different question from Dennis. And he's interested in your thoughts, in your introductory remarks about drug recommendation. How do you propose to model and evaluate the relationship between genomic information and chemical compounds in seconds to minutes?
Okay, that's a great question, basically. So the proposal is, so certainly I don't have the system at the moment, but many people in the world are actually working on different components of a pipeline like this. Certainly you need to learn over time, right? You need to really do these genomic analyses over time and build an understanding of a model or database, let's say, if you want to think from the perspective of a databases. You want to essentially have a corpus of information where you can query when you really need to. So I'm not suggesting the learning needs to be done real time. It can be done over the course of days or years, etc. Because you need to build this information about what to do under what circumstance. But the querying itself, let's say a doctor gets the information about a patient through genome analysis, through everything else they observe. They put all of that information to a, let's say, query system or intelligence system, for lack of a better word. And that system should be able to do that query on huge amounts of trained data and should be able to output a recommendation or maybe multiple recommendations with different levels of confidence in seconds or minutes, in my opinion. So I'm not, the building of the system can be done over time offline and incrementally updated. But when the doctor needs that information, they should be able to input that information and get the results within seconds or minutes, let's say. Whatever is really tolerable for the, given the urgency of the potential situation that the doctor is dealing with. Hopefully that's clear.
Thank you so much for your answer. I have a question from Yen Hume. Will NVIDIA GPU have the same problems?
NVIDIA DPU, right? If I understand correctly. It's the data processing.
It says GPU, but...
Wait, it says a GPU, graphics, G as in graphics?
Yeah, that's what it says.
Okay, sure. Because NVIDIA also has DPU. That's why I wanted to I wanted to confirm. NVIDIA has actually CPU, GPU, and DPU. So the question is about GPU, which is graphics. And yes, absolutely. And NVIDIA GPU has exactly the same problem because it's also also an example of the processor-centric paradigm. So what a GPU does is it has a separate memory chip, and it needs to bring the data from the memory chip inside the GPU caches, as well as the scratchpad memory, internal memory, so that it can process it. And in fact, the register files. So it's no different from the perspective of where data is processed, memory versus the compute unit. It's no different from an existing processor. An NVIDIA GPU has this problem, an NVIDIA DPU has this problem, and a machine learning accelerator has this problem. All accelerators and all processing elements that we build today actually have this problem because memory chips do not have the capability to do computation today. And thank you, that's a good question.
And it was our final question. Thank you so much for your talk, Onur Mutlu.